My name is David DiCarlo. During this session, I'm going to talk you through how I fulfilled one of my childhood fantasies by building my own combat AI. I named it the TRAC AI Library. So specifically during this session, I'm going to talk you through, TRAC AI Library, or TAIL for short. So today I'm going to talk you through what TAIL is, how you add TAIL to combat simulations, and then I'll talk through the first example of me using it in the real world. Before I get into that, let me give some background on AI just in case you're not as familiar with it. So in the past few years, AI has been routinely in the headlines. We've been able to make more and more complex AI. It's been beating humans at everything from Go to games like poker, and now even complex video games like StarCraft. And whenever you see a news article about AI, most of the time, the type of AI that they're talking about is reinforcement learning AI. And I'll talk more about how reinforcement learning works on the next slide. However, it's not that easy to take advantage of AI in our combat simulations. A lot of the simulations made at TRAC were developed before the renewed interest in AI. And in order to have an AI work with your simulation, you need to be able to pass it information, known as the state space. And that can be tricky to accomplish. So I set out to try to find a way to do this. Now, on the next slide, I'm going to go through an example of how reinforcement learning works. But first, let me cover 3 key definitions that you'll see throughout this presentation. The first is state space. So when you're talking about artificial intelligence, the state space is the collection of every possible situation your AI agent could find itself in. Your action space is the set of every possible action your agent can take in a given situation. And then your policy is a mapping between the two. For every situation, a policy dictates which action you should take to achieve the best possible outcome. So let me talk through an example of those to help paint the picture better. So what you see on this slide is an example of a maze where, let's say you have an AI that's been tasked to learn how to get from the start tile in the top left to the end tile in the bottom right corner. In this example, your state space would be the collection of every square the reinforcement agent could eventually find itself in. Your action space are the 4 directions the agent could move, up, down, left, and right. And your policy is what you see in the filled-in grid, a mapping from every square to the direction that the agent should move next if it wants to make it to the end tile. Now, what sets reinforcement learning apart from other types of AI is this notion of a reward signal, that the AI is either given points or penalized based on the outcomes it achieves. So if I wanted to make a reinforcement learning agent that could get from the start tile to the end tile, I could award it points every time it gets closer to the finish line. If you make an agent like that, you'll find that it will eventually learn how to make it to the end tile, but it's going to take the most roundabout, loop-de-looping path you've ever seen, because as long as it eventually makes it to the end, it would get full points. This is where the art of reinforcement learning comes in that you have to try to force the agent to act rationally. So in this situation, you'd find that the only way to get your AI to take the optimal route, highlighted in green, is to take points away the longer it stays in the maze. And as I said, often when you're working with AI, it's an iterative process because you'll create what you think is a rational reward signal. And then the AI is just going to do something nuts, and you're going to have to try to beat it into submission by tweaking the reward signal. And you'll see me come back to this as I talk about my first use case with TAIL. But that's reinforcement learning. So let me talk briefly about what TAIL is. So TAIL is a file-based communication framework used to plug AI into existing combat simulations. Now at TRAC, we use the output of our combat simulations to inform billion-dollar decisions. So one of my objectives as I was building this out is to make sure that nothing I did would compromise the integrity of our simulations. So I tried to make it as loosely coupled as possible to minimize risk to our simulations. And I was pretty successful with that, which had a fringe benefit in that there's no longer a training burden associated with TAIL either. By which I mean, if you just want to experiment with AI, you don't need to know anything about the underlying combat simulation to use TAIL for experimentation. Or if you're a simulation developer, you don't need to know anything about AI in order to plug an agent into your simulation using TAIL. TAIL is set up so you can have multiple agents running at the same time. And you'll see me come back to that and why that's important later on. But on this next slide, I just have a graphic showing how all this fits together. So as I mentioned, in TAIL, you have two main types of users. You have the AI practitioner that adds new reinforcement learning techniques they're interested in into TAIL for experimentation. And you have the M&S developer who need to define the execution logic, which is how to run the simulation and how to read the output, as well as the decision logic, which consists of that state space, action space, and reward signal. Once both users have done their job, TAIL can be used to solve one or more decision problems inside a simulation simultaneously. But that's an explanation of what TAIL is, not why someone would be interested in using it. So let me hit on that briefly. What makes TAIL useful is that it allows you to automate decisions that normally a human would have to do by hand. So take, for example, say a modified game of chess, where at each turn in the game, you had to move every one of your pieces on the board. Eventually, that'd get very tedious because you're going to be doing about the same thing with your pawns every time. With TAIL, instead of moving each of those pieces individually, you'd be able to specify the effects that you want to achieve. So you could say something like, I want to take that knight, or I want to defend my queen. And the AI would automatically figure out the best way to accomplish that objective and move all the pieces for you automatically. That can save a lot of time as you're setting up combat or complex scenarios in our simulations. It can also let you layer on complexity and create more realistic situations in less time. Before I get into my use case, let me talk about what goes into adding TAIL into a combat simulation. For an M&S developer, as I alluded to, it's not that easy. So inside of TAIL, there are 5 interfaces that you have to implement in order to integrate TAIL with your simulation. As I said, you have to define how to run the simulation, how to interpret the results. You have to define a state space, an action space, and a reward signal. And that's not easy. I almost failed to accomplish that the first time I used TAIL, and I wrote the library. However, TAIL exists as its own code sandbox. So as I was trying to figure this out, I didn't change a line of code in the underlying simulation. In fact, the only interaction between TAIL and the M&S is an optional interface called a policy actor, which you'd use if you want the AI to learn on the fly and actually get smarter as your game progresses. If you're fine having a pre-trained AI that already knows what it's going to do, you don't need to modify a single line of code. And that's the route I took in my first use case with TAIL. The other role inside of TAIL, as I mentioned, is the AI practitioner. They have a much easier job. There's only one interface that an AI practitioner would have to deal with, which is called optimization engine, where you need to explain how your AI explores the state space and how it generates a policy after it's done training. And that's not even required anymore. A year ago, I worked with one of our summer interns to create a direct linkage to a library called OpenAI Gym that I'll talk about more at the end of this briefing, so that we can directly import complex reinforcement learning agents. So now let me talk about the first time I used TAIL. The first time I used a TRAC simulation named Logistics Battle Command, or LBC. So LBC represents sustainment operations on the battlefield. And one of the things that can play out is sustainment convoys going out to resupply units, and those convoys being ambushed by hostile forces. Inside of LBC, there are 2 types of ambushes that can take place. The first is the harassing attack. In a harass attack, the enemy forces will surprise the convoy. They'll quickly try to take out as many supply vehicles as possible, and then they will run away before before the convoy can return fire. The other type of attack is an annihilation attack. In this case, they're going to try to completely destroy the convoy. They'll focus first on the armed guards, and they're only going to withdraw after they sustain some predetermined level of casualties. Originally in LBC, there were 3 ways to set up ambushes for a simulation run. The first would be to hard code it for the entire scenario. So you can say, okay, during this game, we are only ever going to do harassing attacks. The second way would be to assign a probability to it. So anytime there's an ambush, roll a die, 60% chance it's going to be an ambush without actually looking at the different forces involved. The third way would be to script it, to go to each ambush that was going to happen in the entire scenario, and for each one, manually decide what type of ambush was going to take place. So when I found this representation in LBC, it seemed like a great opportunity to use AI to take over. So this is when I decided to make an ambushing AI. The first step to do that was to redefine it as a tail decision problem, which means the state space, the action space, and the reward signal. So in this situation, for my state space, I worked with the LBC developers to define 4 attributes that you can see on this slide that together created over 1,300 different ambush situations that the AI could discern between. For my action space, I came up with 7 different types of attacks, ranging from leave the convoy alone, to harass, to annihilation attacks with different loss thresholds. The reward signal is what you see in the middle bullet. I had to iterate a couple times to get the AI working the way I wanted. But in the end, I wound up giving it 1 point for every supply vehicle it destroyed, 10 points for every armed escort it destroyed. Then I gave it a large bonus if it forced the entire convoy to abort its mission as a result of this attack. And then to prevent the ambushers from being too aggressive, I scaled back the reward and gave a penalty based on the number of losses that the ambushing force sustained during the attack. The result was I had created an ambushing AI that would try to conserve combat power until it saw a large convoy it could overwhelm. Then it would commit itself to heavy losses in order to force it to abort. Now, everything you see in blue on this slide is a knob that you can turn to adjust the behavior of this AI. And as I mentioned in the beginning, Tail can handle multiple agents operating simultaneously. So say in my simulation, I wanted to have a very aggressive ambushing force in one corner of the map and a conservative force operating in another corner of the map. That's easy to do in Tail. You just create 2 agents with 2 different reward signals. You can also update the reward signal on the fly. So let's say halfway through the simulation, conditions on the battlefield are less favorable for the enemy forces, and they decide to start acting a lot more aggressively. You could easily accomplish that by just on the fly reducing the penalty for taking losses, and the AI will learn to act more aggressively to match this new reward signal. So it's very useful. And as you can imagine, it lets you add a lot more complexity into your simulation with a lot less time. Now, because TRAC is focused on analysis, we want to make sure that everything we're doing is acting rationally. So Tail helps you do that by creating table-based output for everything happening under the hood. The 2 most important output files that Tail creates are the policy file and the transition file. The policy file you see in the lower left corner of this slide, it contains the policy, the mapping from every possible ambush scenario to the best type of attack that enemy forces should launch. The transition file contains all of the experiences that Tail had while it was learning the optimal policy. Now, as a human, I can go back and forth between these 2 files to figure out exactly why my AI is acting the way it is. So take, for example, the rows highlighted in blue, starting with the policy file. Let's say I was curious as to why for this situation, my AI thought that it would be best to launch an annihilation attack with a 50% loss threshold. Maybe I think that's way too aggressive. I can take the ID for this situation, which is 2048, and go into my transition file where I can find all of the training experiences associated with state 2048. Scrolling down that list, I can see that for action ID 4, which is the 50% annihilation attack. It's the first time the AI managed to force the game into state 1892. I don't have it pictured on this slide, but state 1892 is much more advantageous for the ambushing force to be in, which made Tail think that it was worthwhile to take the additional risk of casualties. Now, as a human, I can go in and see this and say, okay, I understand why you did that based on the reward signal I gave you, but I don't think that's what a rational human would do. So I would go back and I'd tweak my reward signal to stop it from thinking this is the best route. And that's the feedback loop where I was talking about the art of reinforcement learning. Using these files, it's easier to quickly iterate with your reinforcement learning agent to beat it into submission, so it starts acting the same way you would given the choice. So once I was comfortable that my AI was acting like a mini-me, I let it loose in an actual LBC game to see what would happen. And in hindsight, I should have expected it. I had only given intelligence to the ambushing force, not the convoy. So when I let my combat AI loose inside of an LBC run, it was devastating. The ambushing forces were achieving exactly the results they wanted to achieve, exploiting every weakness they identified during their training. And the convoys were just going on their merry way. They had no way to respond, so they just kept presenting the same weaknesses again and again for my AI to exploit. And although it made me feel like a proud father seeing what an agent of chaos I had wrought, it was not useful for analysis because that is not how things would actually happen on the battlefield. The key takeaway from that was that if you're going to add AI to an adversarial decision, you need some form of intelligence on the other side as well for it to be worthwhile, either another AI or a human for it to play against. It's a lot more straightforward to add AI to non-adversarial decisions, such as convoy routing, which is one of the next directions I'm going to try to take Tail inside of LBC. Now, Tail doesn't operate in a vacuum. This is what I made for TRAC, but there are similar frameworks out there. So one that I want to hit on quickly is called OpenAI Gym. This is available on GitHub. Gym is a Python library that's used to test state-of-the-art reinforcement learning techniques. It tests them against pre-packaged environments. Now, inside Gym, an environment consists of a state space, an action space, and a reward signal, just like a Tail decision problem. So as I mentioned, this last summer, we actually had one of our summer interns help me out to create an adapter between Tail and Gym so that you can pull any reinforcement learning agent off GitHub that's been designed to be tested against Tail and plug it directly into our combat simulations using Tail as the communication layer. I'd say this effort's probably about 40% there. We've demonstrated that it can work, but there's still some refinements we can make so that we can make best use of those agents that we pull off GitHub. So yeah, in summary, I created the TRAC AI Library, or Tail, as a way to connect our combat simulations with modern reinforcement learning AI. I used it in LBC in order to create a ambushing AI, but since this original effort, TRAC Monterey has continued AI in combat simulations. That's the presentation you're going to see next, where I helped create the integration layer for that project using the concepts of Tail in a different simulation called VAST, so that we create a move and shoot AI. That's all that I was planning to present today. Thank you for your time. I'd love to hear any questions you have about this.
Hi, David. This is Cheeto at TRAC-WSMR. How are you?
Hey, I'm doing well.
Hey, interesting talk. I was just wondering if you think that this thing is not just suitable for LBC, but maybe for AWARS or Combat 21. I'm not sure how familiar you are with those models, if you feel this type of methodology would be good for that as well.
It would be perfect for Combat 21 and pretty easy to integrate because I believe both LBC and Combat 21 use the same discrete event simulation as their backbone.
Okay.
So a lot of the code's already been written there. A-Wars is harder
Oh, is
because
it?
it's C++ based.
Oh, okay. And I didn't mean to leave OneSap off. You think this would work also with OneSap?
Yes, I do, which is interesting because there's actually a lot of contracts out there right now trying to add AI to OneSaf.
Oh,
I probably have a leg up with if I were to use Tail towards it.
oh, that's cool. Okay. All right. Well, thank you and appreciate your talk again. It was very interesting.
Thank you.
Do you use Python mostly, or what other coding languages do you use?
Oh yeah, so that's interesting. So Tail is actually written in Java, but we have a Python adapter because most of a lot of the recent reinforcement learning agents are all Python based. So Tail is both. The integration code is in Java because simulations tend to be written in Java or C++, and that makes it easier to integrate. But it bridges to Python and can execute Python from inside Java because that's where all of the current AI are.
Wow, okay, thank you. That's interesting.
Yeah, it was this whole ordeal to create that communication layer, but it's pretty cool now that it works. Nothing else?
Oh, hey, David, it's Cheeto again. So the tail is based on planning. That's what it's doing internally?
So Tail can do anything. I started with planning because I thought planning made most sense for analysis. You don't
Right.
want a learning agent representing a kernel who already knows everything he's going to know. But yes, it can do live learning if you want it to.
Okay. I don't know. Have you seen anything on Vader? I don't know if you've heard about Vader because I think it's still on its initial kind of cut.
Just that it's making it to made. That's all
Yeah.
I know about it.
Oh, yeah. Yeah, it's one of the ones they're trying to put in there. But and it's more of the, hey, what can we use at a MapX to kind of let people put information in? But it also seems like it would be a good way to give the high level goals for a scenario. And then, if you use planning between the goals or obviously to achieve the goals, maybe you could do an automated system that could generate a scenario for Combat 21 or LBC or OneSAF or A-Wars in the end. And I wondered if Tail, maybe at some point you could look at Vader a little bit and see if like maybe it could be used in that situation as well to actually generate the scenario.
Yeah, that would be fun. This is a fun project to work on because I like AI. So if I have opportunities, I'll take them.
Okay, yeah, we'll keep you in mind because they're giving a lot of presentations on Vader. If it comes up again, I'll see if they can put you on the invite so that you can take a look.
And that reminds me of something else I wanted to bring up, is that Tail has been a popular project for our summer interns. There have been two in the past 2 years. So one came in and added genetic algorithm learning, the Tail's repository of techniques it could use. And then the other I mentioned added that gym adapter. But as long as Tail lives, it's going to continue to be a good opportunity for summer interns who want to experiment with AI.
So I'm just a student at NMSU, and I've never really talked about AI or anything recently or at all. And I was wondering, so is this Tail program used to perfect a combat scenario, or is it used to help create combat scenarios? I was a little confused there.
So the way it works right now is normally you'll have a human figuring out what's going to happen in the battle. Like, okay, we're at hour 5 of the scenario. The battlefield looks like this. What are each of the units going to do? It can take a long time to set all that up. So Tail, you just tell an AI, okay, these guys are supposed to defend, and it will figure out how to move all those guys for you. So it helps, like going back to the chess example, it helps save time so you don't have to move all the individual pieces.
Okay, awesome. Yeah, that makes sense.
All right, well, thank you, David, for your time today.
Yeah, no, thanks for having me.
I think
thank you.
Yeah, I think we'll go ahead and take our break unless anybody else has any questions. If not, we'll be coming back at 1:45.
I just wanted to say thank you. That was really interesting. I really enjoyed that.
Yeah, no, thanks for saying so.